Hey guys, John Polemy here, Actionable Intelligence. And today I want to go over a paper that I read on the Manhattan Institute website. The name of the paper is Mines, Minerals, and Green Energy, a Reality Check. And it was written by Mark Mills. I'll put a link to it in the show notes. I suggest you read it. He has other good papers too, talking about talking about green energy transition and exercise and magical thinking. But I basically have my title here for this presentation. If you love renewables, you have to love mining. You know, I've said it many, many times before. I don't think people really understand what goes into um, all the things that we take for granted and the supply chains and the amount of mining and growing of things that's required to give us the lifestyle that we have. And so that's part of what I'm trying to do here. I'm going to show you that, or at least go over this paper where Mills has shown, and it's footnoted, so you can check the footnotes if you'd like. Don't argue with me; it's not my paper. But the point is that regardless of what you may think about renewable energy, green new deals, all this stuff, I'm not going to get into that. What I'm going to show you, though, is that if we go down this path, the tremendous amount of materials that will be required, and that's not being discussed. And I think that represents an opportunity and is actionable. So the first slide here, it's in quotes. These things are from the paper, and I do quote quite a bit. Denial is not a river in Egypt. That's my title. Many enthusiasts, he's talking about renewable energy enthusiasts, believe things that are not possible when it comes to the physics of fueling society, not least the magical belief that clean tech energy can echo the velocity of progress of digital technologies. It cannot. We went over this with Dr. Michael Kelly from Cambridge, who's professor of engineering, retired. And this is exactly what we were talking about. People conflate the progress that's been made in electronics, that's been made in computer chips. You know, Moore's law does not apply to batteries and does not apply to wind turbines. Uh, you're not going to get, like you do in microchips, a doubling in the power of a microchip and then a halving of the cost every year to 18 months. That's not going to happen for various reasons. There's for wind turbines, there's Betts's law talking about the amount of wind that can be converted efficiently. There's other physical laws that come into play at some point. And so the idea that we just need to scale this up and commit to it and it'll happen um, is limited by some physical constraints of the real world. This is one of the paragraphs I like the best that I've talked about in the past, and I think this is very important. All energy producing machinery must be fabricated from materials extracted from the earth. No energy system, in short, is actually renewable. Since all machines require the continual mining and processing of millions of tons of primary materials and the disposal of hardware that inevitably wears out. Compared with hydrocarbons, green machines entail, on average, a tenfold increase in the quantities of materials extracted and processed to produce the same amount of energy. And this is why they have to be mandated and they have to be extremely subsidized. Okay, we'll go into another slide, but there's a reason why they used to use windmills in the Netherlands in the 14th, 15th, and 16th centuries, 17th centuries, all the way up when they were, reclaiming the land from the sea. They would use windmills powered pumps. But when the steam engine came along in coal power, they stopped using windmills. They're museums now. They don't grind grain in the Netherlands with windmills anymore because it's not efficient. This means that any significant expansion of today's modest level of green energy, currently less than 4% of the country's total consumption versus 56 from oil and gas, will create an unprecedented increase in global mining for needed materials or minerals, radically exacerbate existing environmental and labor challenges in emerging markets, where many mines are located, and dramatically increase U.S. imports and the vulnerability of America's energy supply chain. So this is very important. This kind of brings to mind the whole scandal that came up several years ago and still is around to a certain extent, where various energy companies, renewable energy companies, battery makers, mobile phone makers, i.e., Apple, were being castigated in the press because of the child labor that was used in the DRC to mine cobalt, artisanal cobalt. And of course, they've all pledged they're not going to do it. You will talk with activists and they'll say, well, it's not happening anymore, but it is still happening. It's not the major supply of cobalt, but it's still happening. And a lot of these mines where these places are, where these minerals are available, are emerging or frontier or developing markets. So, one of the things that I can't get square in my mind with a lot of the environmental activists is they don't have an issue, or they turn their head and don't look at some of the practices that go on in some of these countries around environmental degradation, the way that the mining is done, how the contracts are signed with the government, and what the real true benefit is to the people. Because we need to green in the West, and we're not going to look at that. So if you're creating, all this disruption, if you're creating environmental degradation, but you can't see it, it's still there. Is that morally and ethically correct? I mean, that's just a rhetorical question. I'm not going to get into that. I'm just telling you that it does exist. And you're moving tremendous amounts of earth to get these materials, and they're not in easily accessible areas. So let's talk about the scale of the task a little bit. The paper does this. This is what I really like about it. And like I said, I encourage you to read it. Link will be in the show notes. So let's get into some examples here that are in the paper. Replacing the energy output from a single 100 megawatt natural gas fired turbine, itself the size of a residential house, producing enough electricity for 75,000 homes, requires at least 20 wind turbines, each one about the size of the Washington Monument, occupying some 10 square miles of land. Building those wind machines consumes enormous quantities of conventional materials, including concrete, steel, and fiberglass, along with less common materials, including rare earth elements such as dysprosium. A World Bank study noted what every mining engineer knows. Technologies assumed to populate the clean energy shift are in fact significantly more material intensive in their composition than current traditional fossil fuel based energy supply systems. And so if you're listening on the podcast, you won't be able to see this, but I'm showing a chart right now that shows the materials requirements to build different energy machines. And what we see along the bottom, there's bar charts here, 5 of them. You see solar PV, hydro, wind, geothermal, and natural gas along the horizontal axis, and on the vertical axis you see the materials used in tons per trillion watt hours. And the highest material requirement for trillion watt hours is 15,000 tons of material for solar PV. The next intensive is hydro, third intensive is wind, the fourth geothermal, and the last is natural gas. And you're talking about tremendous usage of steel, glass, concrete, and cement. Now, it goes without saying that steel, glass, and concrete production from raw materials are very energy intensive industries. As a matter of fact, I saw a chart last week. I didn't put it up and I don't have it available for this presentation. But you can do some research on this if you are so inclined. But some of the largest emitters of CO2 are these industries of steel, glass, and concrete. And these are, tons and tons of this material is required for these energy making machines, or energy harvesting machines, if you will. The argument is, well, we'll just recycle it. Well, that's true. They are into, in wind power at least, they are into a concept, at least here in the United States, that's called repowering. And that is where you take a turbine that's, or a wind farm that's been around for, I don't know, I've repowered sites that are 15 years old. Some I've seen at 12 years, 20 years, whatever. And you either take the old machine completely down, which we just tipped them over at one site. We just cut it with an exothermic cutter at the base and pulled it over with an excavator, came crashing down. And then we picked up all the materials, cut it up, the steel, and scrapped it, scrapped out the generator with the copper. And then the blades, which are made of fiberglass, were just cut up and put in a landfill. And I can tell you that it was an extreme discussion with the landfill operator about putting all those blades in the landfill. They take up a tremendous amount of space, and landfill space, depending where you are, is prime real estate. And to filling them up with fiberglass blades that are going to take, I don't even know if they can decompose over thousands of years. I have no idea. I know it was a big problem for this landfill. They didn't want to take them. So that's another thing you need to look at. We're just going to recycle everything. It's not going to be like growing trees and burning biomass where it's like this circular thing that just happens. I mean, there's energy that's required to do all recycling, to process, and it's not profitable to do that currently. It's cheaper to mine new material than to go out and just recycle these things. So, cost does matter, whether people want to realize or not, because ultimately the cost is borne by the energy consumer. I mean, if the project costs twice as much than what a gas turbine costs, the ratepayer, the person consuming the electricity, has to pay the amortization costs of that plant over its life, along with the interest costs for the debt that was used, along with some margin of profit. I mean, things aren't done at a loss, typically. So a tremendous amount of material is needed, and it's shocking when you look at this chart because a natural gas combined or gas turbine is to the far right uses, like on this chart shows, like 1/20th of what a equivalent solar PV installation would use for the same amount of terawatts that were made. Something to think about. So I'm just talking here on this slide, the scale of the task continued. The paper goes on to say, the handling and processing of such large quantities of materials entails its own energy costs, as well as associated environmental implications. But first, the critical supply chain issue is not so much the increase in the use of common, though energy-intensive materials such as concrete and glass. The core challenges for the supply chain and the environment reside with the need for radical increases in the quantities of a wide variety of minerals. What you're talking about there is a lot of your rare earth minerals, okay, things that you don't typically think about that are used in the magnets and brushless motors and things like that. The world currently mines about 7,000 tons per year of neodymium. For example, one of the numerous key elements used in fabricating the electrical systems for wind turbines. Current clean energy scenarios, imagined by the World Bank and many others, will require a 1,000 to 4,000% increase in the neodymium supply in the coming several decades. Well, that's just not magically going to happen. I mean, I haven't looked at the U.S. Bureau of Mines and people that gather this data, but does this material exist in the quantities necessary? Where does it reside? Is it in an area that can be mined efficiently? There's a lot of times when I'm investigating a mining company and they'll have a tremendous asset, but the thing's in the middle of nowhere. There's no infrastructure, there's no roads, there's no people living near it, and all that has to be built. That's part of the cost. So you're starting to get a picture for some of this. This is a tremendous amount of work to get this stuff and cost. The mining of indium used in fabricating electricity generating solar semiconductors will need to increase as much as 8,000%. The mining of cobalt for batteries will need to grow 300 to 800%. Now, I know after the big battery day, the Tesla homers will get on here and say, well, Elon got rid of cobalt in batteries. Well, not yet, he hasn't. And that doesn't mean they're going to go away. Cobalt is in those batteries for a reason. It keeps them stable because you have a tremendous amount of energy you're shoving into these things, and the cobalt is what helps keep the battery stable and keeps it from catching on fire, and they still catch on fire anyway. So if you're reducing the amount of cobalt or removing it, hopefully you've come up with another material or chemistry that will lead to a more stable battery, or at least as stable battery. That's why they use cobalt. Lithium production used for electric cars, never mind the grid, will need to rise more than 2,000%. And so where do you get a lot of this lithium? It comes from these underground brine mines in the middle of the desert, in Chile or Bolivia. I mean, they're taking this stuff out of the ground, this brine, this liquid that's mixed with all these minerals. They're spreading it out in these large pools and containments, and then they let the sun basically beat down on it for some period of time, and the moisture, the water, the liquid component of the brine is evaporated away, and then you're left with the mineral components, which then have to be processed, which is energy intensive, have to be transported, and have to be fabricated. The Institute for Sustainable Futures at the University of Technology, Sydney, Australia, last year analyzed 14 metals essential to building clean tech machines, concluding that the supply of elements such as nickel, dysprosium, and tellurium will need to increase 200 to 600%. I don't even know what some of these things are, but evidently they're required to make these machines. And if I don't know what they are, I don't know what, like I said before, quantities, are they in concentrated quantities? Are they a byproduct of some other mining? I don't even know this. And just to say that you're just going to increase something by 300 or 400% or 800% over some period of time, you know, that's a statement, but that doesn't mean that that's a plan to do it. The implications of such remarkable increases in the demand for energy minerals have not been entirely ignored, at least in Europe. A Dutch government-sponsored study concluded that the Netherlands' green ambitions alone would consume a major share of global minerals. Quote, exponential growth in global renewable energy production capacity, the study noted, is not possible with present-day technologies and annual metal production. So this is your opportunity. Dr. Kelly said the same thing in his discussion of the UK. He went through the numbers and said if you tried to electrify transportation in the UK, you would consume a majority of those necessary minerals. World production just to do the UK. So now the Netherlands has said if they try to do it, they'll consume the majority of the minerals necessary. The UK has said the same thing, and yet everybody's pushing forward and hasn't secured the supply chain. That looks like an opportunity. You will recall that in a previous video, like a couple weeks ago, I told you that these auto manufacturers are spending hundreds of billions of dollars to push forward on electric vehicles. Where are they getting the materials? If they're going to build millions and millions of cars, tens of millions of cars, where are they going to get the materials? Now, the wags out there will say, well, somebody will figure it out. They'll figure out a substitute or technology, but they haven't figured it out yet. That's the point. And yes, I agree that technology does advance and science will advance. But in the end, physics and chemistry are what they are. And some things you cannot engineer around. So in the paper, he talks about just the components that are needed for electric car batteries. And what he says at the top is 500,000 pounds. That's the total materials extracted and processed per electric car battery. And I'll explain that as I go through this. For example, lithium brines typically contain less than 0.1% lithium. So that entails some 25,000 pounds of brines to get the 25 pounds of pure lithium. This is per electric battery for a car. Cobalt ore grades average about 0.1%. Thus, nearly 30,000 pounds of ore are required to get the necessary ore, or cobalt. Nickel ore grades average about 1%, thus about 6,000 pounds of ore are required to get the necessary nickel. Graphite ore is typically 10%, thus about 1,000 pounds per battery. copper at about 0.6 in the ore, thus about 25,000 pounds of ore per battery. Well, if you add all this up, it doesn't come up to 500,000 pounds. So what are we really talking about? Well, when you're mining, the ore isn't an ore body. It can be near the surface, and you would use open pit mining. It could be deep underground, and you would be doing some type of underground mining. And what we're saying here is that in order to get to the ore body, in order to get to the good stuff, you have to take off a tremendous amount of overburden if you're on a surface mine. Overburden is just dirt and material that has to be moved so you can access the ore body. Same things underground. You have to tunnel down, you have to build service shafts, hoisting shafts, ventilation shafts. Then you get down to the levels in the earth where the mine is, or where the ore bodies are, and then you have to go out on the horizontals to the ore bodies and mine them through various techniques. And there's a tremendous amount of waste rock, okay, that has to be moved and processed and crushed in order to get the necessary ores and minerals that you are seeking. And this is not cheap. You know, I'm talking about, for example, like in Mongolia, the Oyu Tolgoi copper mine that Rio's building. They're spending like almost $5 or $6 billion on the underground portion of the mine, and they really haven't even really begun big, large-scale mining yet, and it's running into a lot of issues and delays. You know, mining is not some easy thing like just building a house in 6 months. I mean, you get into these situations where I said before, you have a political component, there's environmental components, there's financing, there's procurement. You have to build the mine. Then you start running into unanticipated consequences or issues that you didn't anticipate. Then you could have a change in the politics in that particular country or government, which seeks to extract more money from you because you now have a fixed asset in their country. What are you going to do? Pick it up and take it? So there's all of these things that go into this that no one thinks about. They just go, "Oh wow, man, Elon Musk is such a genius. He's gonna build millions and millions of Tesla Model 3s a year at $25,000 a piece." And no one understands or cares or thinks about how you're going to get all the materials for this stuff. Same thing being said about solar panels and wind. Now, we've built out our energy infrastructure. We have a sunk cost, but it's taken, 150, 200 years, or 150 years at least, and tremendous amounts of capital. It's a big sunk cost. You're just not going to replace that, in 2030 by having some former bartender get up and scream about the world's going to end. It's just not going to happen. So, I think I look at those things as, just the rantings of, ideologues and people that are trying to move the Overton window and move the discussion in there to their side of the argument. But if we push forward, like California, many states in the United States have minimum renewable standards. That's why the utilities have no choice. The utilities don't care. They will put these things up because in the end, the ratepayer pays. All the costs are passed through to the ratepayer. These are regulated utilities for the most part. They could care less. And they know that they will have to build gas turbine plants or other spinning reserve in the background for when the time that the intermittency of the um, renewable source is not present. So what I'm saying is this is a tremendous opportunity because it seems like we're going to go down this path. It's to some extent. And even if we try it at any scale, there's going to be a tremendous demand on the mining industry. And the mining industry has been starved for capital, just like the oil and gas industry has been. And people don't recognize that. So if there's a big push, which I suspect there will be, especially if you get a Joe Biden presidency and a Democratic Congress, there will be a huge, huge fiscal spending initiative, and will be focused on green energy. And they're going to find out very quickly. It's not even just it's funny because it's not even just the materials in the ground. You can't even get cranes right now in the U.S. to build these things. It's hard to get cranes. It's hard to get the necessary trucks and trailers to move the blades and the components. And if you want to scale this thing up, now it can all be scaled up, but it takes time and it takes money and it takes materials. And those materials and machines wear out over time. They have to be replaced. So what I'm telling you is that regardless, if the economy comes back and we have eventually get past COVID-19 and the restrictions, the economy's coming back, you look at the Purchasing Managers Index, the demand for materials is going to increase. If you throw on top of this these physical programs that I believe are going to come out, whether regardless of who gets elected, you're going to have more demand. And if you try to go down this green thing, it's just going to be tremendous for some of these areas because the materials just aren't scaled up. Not to say they won't be, but the prices are going to go nuts. So I put a couple pictures in here because I don't think people really understand. You talk to people that are talking about. I'm showing a picture here now of an open pit copper mine. Doesn't matter which one it is, but you can see the huge hole in the ground at the top of the picture. Then you see the road and rail to the mine or to the processing facility. You can see where they crush the material, and you can see the thickeners in the lower left hand corner where they separate out. It's probably a copper mine, it looks like. But I don't know if they're doing smelting there too, but you see the smokestack with the pollution. This is kind of a interesting, where is this? I don't even know, but you see this huge hole in the ground, this big scar. And, there's a cost environmentally to everything that we do. There's no free lunch. And if you want to have the lifestyle that you have now, people use a certain amount of materials. It requires digging things out of the ground. And increasingly, that means places that emerging markets. I mean, are you going to go and be able to open up mines in Canada and the United States the way the governments are going? What about Europe? So increasingly people are going to be looking to developing markets, places where they can go, where the governments, shall we say, may be more pliable or more open to allowing these activities. And then what kind of environmental controls, what kind of, environmental health and safety rules are in place? What kind of labor laws? How much does the populace there actually benefit? I mean, you get your Tesla and new iPhone, but what do they get? The other thing I wanted to point out, I show another picture here of this another mining operation, and it shows a big bucket excavator and a big haul truck. Now, these things don't run on wind power and solar panels. These are fueled by diesel engines, and they consume a tremendous amount of fuel. Depending on how big that haul truck is, it's probably maybe getting a half mile per gallon when it's fully loaded, or maybe less. And that excavator is consuming, I mean, a pickup truck wouldn't even come up halfway on those tracks on that excavator. That's how huge these things are. And so this is what's required. These things are not, this is what it means to go into the earth and pull these materials out and removing tremendous amounts of rock and overburden and associated material just to get to these small amounts. Remember what I said earlier, with copper, it's only 0.6 of the percent of the material you pull out actually has copper. The same thing with nickel. For every 100 tons of material that you remove, you get 1 ton of actual nickel, and that still has to be processed and purified and then fabricated into whatever you're going to make. So I will put a link to this. I think regardless of how you want to look at it, you're going to have to be an advocate for mining if you want to have the move in this direction. You're not going to get away from it. And then you start talking about zero carbon footprints. I mean, it's just, I don't think people really understand what's going on. I could go down the rabbit hole and say, well, they know that they can't do that, so why are they really doing this? Well, is it because maybe they want to create the narrative and move the Overton window to a place where, well, we really can't do this, but carbon's still a thing, so now we have to constrict your way of life. We have to raise the cost of energy and everything else, put a carbon tax on everything to make you not use as much. I mean, that's what they do in Canada right now. They have carbon taxes. They're talking about throwing another carbon tax on. I mean, I don't live up there. Maybe one of the Canadian viewers can school us up on what that means on their bill every month. on their heating bill or their electric bill. But I have some knowledge that's what they're doing there, and that's what they're planning on doing in Europe, and I'm sure the United States, with the right political climate, would move in that direction. So a lot of things to think about. It's not just, hey, that's really sounds great. I'm all for clean air and clean water. I'm all for renewable energy. What does that really mean when you start talking about it? What does that entail? All right, guys, that's it for this video. Appreciate it. We'll talk to you next time.